Hello, Jacob. Thank you for joining our podcast. Today, our guest is Jacob, CEO and co-founder of Maxwell Labs. I would like to start with a question. Could you please tell us the story behind Maxwell Labs? How did the idea for photonic cooling come about?
The inception, the idea behind Maxwell Labs is essentially stems out of experience from working at Cray supercomputer. So they're a supercomputing company that was sold to HPE a few years back. But these guys basically invented supercomputers, Seymour Cray, and I worked there along with some other folks that are now at Maxwell on estimation, like basically performance modeling. So the idea was to predict how supercomputers were going to perform for a given application on hardware that didn't exist yet, 5 years from now or whatever. And even back in 2015, 2016, 2017, it was becoming very clear that there was serious bottlenecks in getting heat out of the chips that were coming that we weren't prepared to deal with. There's hard limits to how fast you can get heat out of materials. This is known as a conduction barrier. And so the inception of Maxwell Labs is around, we know there's only two ways to move heat around. Physics kind of constrains how we can move heat. And the two approaches are atoms banging on each other, that's conduction. So atoms vibrating and heat moving through a material. And there's light, there's electromagnetism. And those are your only two options. And so Maxwell is the physicist who kind of invented the theory of electromagnetism, right? So the idea is that we're going to use light to cool. And eventually light is going to be a component of cooling systems. We didn't know how back then. There was ideas, but we were following research out of various groups across the world. And one of those groups was led by Alejandro Rodriguez, who's now our CTO. And it's an interesting story how he got into the picture. But basically, this group was showing that they've been working on these computational tools to figure out what the limits of electromagnetism are. Like, how much energy can you really move around? How much information can you move around using light? And what was clear even back 10 years ago was that the bounds that we thought were in place on how much heat could be moved with light were much larger than we had assumed historically. And so that's where Maxwell comes in, and basically we found a path along with Alejandro as we brought him on as CTO using laser cooling. And laser cooling is a type of it's kind of a weird thing that you can do with lasers, but if people are kind of used to lasers as something that heats up a material, right? They use it to cut materials or whatever you want to do with your laser, but usually it heats things up. But there's special circumstances where you can engineer a material to do the opposite. So effectively, you can push laser light through a solid material, and the material gets colder. And the way this works is you're taking low energy, like you can think of it as red light, and low energy, long wavelength red light. You pass it through a material, and maybe there's some like ions in there that interact with that light somehow. But when they interact with it, they don't spit out the same frequency of light. They spit out a shorter wavelength, a higher frequency light. And so that light is like blue shifted, they say. And that shift, that shortening of wavelength requires energy. And the energy comes from the phonons, the heat energy in the lattice of the material that the light is passing through. And that's how laser cooling works. And you can engineer materials through photonic design, essentially the same thing they did with solar panels and LEDs. You basically put these materials into a thin film, you optimize them using computational tools known as inverse design, this process. And if you do that for long enough and on enough servers, you eventually get a design for something that can turn what is typically very low efficiency laser cooling into very high efficiency laser cooling. And that allows you to go to much higher power densities. And that's what's exciting about laser cooling, is that laser cooling offers the possibility of reaching power densities on chips that are unfathomable today. So typical chips today are tens of watts per millimeter squared in terms of their power density. They have hotspots that are they're unlike anything really humans have ever created. They are the most power dense technology that humans have ever built. They have power densities that they actually are greater than the core of a nuclear reactor. Is a good data point that we like to use for comparison. And that aspect of chips makes them very hard to cool, because it's not like the whole chip is hot. You're dissipating hundreds, if not thousands, of watts from these chips, and the energy how that energy is trying to escape the chip is coming out of microscopic regions the size of blood cells. Like, they're very, very small areas, tens of microns. You're pushing all this power out. And so when you apply typical cooling, you're just pushing air across the whole surface area of the chip. You're trying to use the whole surface area of the chip to pull that heat out. But the only place that matters is where those hotspots are. And that's what laser cooling allows you to do, and at very, very high cooling power densities. And so that means you could, in principle, if laser cooling works to cool chips, you will be able to build chips in the future for the next 100 years, who knows how long, and scale performance, scale that power density to tens of thousands of watts per millimeter squared, not tens of watts, tens of thousands of watts per millimeter squared. And we can't even imagine what a chip looks like that's operating at those kind of power densities today. But if this works, that's what will happen long term. That's the goal anyways. That's what we want. We want faster computers.
Jacob, thank you very much. Very, very clear explanation. Could we speak that your technology is going to make a revolution?
That's the idea. Yeah, that's the hope. Is that we're going to revolutionize performance on computers. Chips have not gotten faster for the last 25 years. What they've done is they've added cores. They've been kind of putting off dealing with this problem of hotspots by just adding more cores and spreading them out to make it more uniform, right? To be able to spread that heat out as best they can, but still getting you additional performance. But what they've done is they put the onus on the programmer. They said, hey, here's all these cores. You guys figure out how to make your algorithms speed up by using those cores, because it's not like you're sequentially speeding. You're not speeding up sequential work. The clock speed of the chip isn't increasing. The parallel stuff that you can do on the chip is what you're increasing by increasing the number of cores, so that you have more compute capability, but you have to be able to exploit it by rewriting your algorithm to take advantage of that parallelism. And that's what AI is doing. That's why AI has blown up, and they're able to kind of come out with a new chip every year. They're just adding more cores into a larger area, and they're mapping these AI algorithms, which scale very, very well in parallel in that kind of an architecture. So this approach works very well for AI, right? But the point is wouldn't you like to have all of those cores, maybe add about 1,000 times more density to it and run it at 100 gigahertz instead of 2? Like, that's what we're after. And so that's what we're going to do.
Okay, got it. I would like to ask you, what the biggest challenge you faced? Maybe, I don't know. I don't have a vision. So in any case, this laser must be placed somewhere near the processor and so on. So I don't know. I'm just imagining.
Yeah. The way the picture to have in your mind here is basically, think of like an array of like LEDs or an array of pixels on a camera CCD, right? You've got a bunch of little cooling pixels that are now set on top of the chip, and those pixels can turn on and off depending on where the hotspots are located, dynamic. And so it doesn't matter what the chip architecture is. It doesn't matter if the chip was built 5 years ago or if it's built 10 years from now. You will be the same photonic cold plate will be able to target and remove those hotspots from the chip dynamically in real time.
Okay, but in any case, could you please tell me? I'm just curious. What are the most interesting moments you faced during the development of this technology? What you had to overcome?
Yeah, I would say the most interesting piece, or kind of like the biggest like change of thinking that we had to go through in the process of developing this photonic cooling technology was the efficiency. Like, what does it mean? Like, we knew that it could do a ton on the performance side, right? It was very clear right away that this is the way to go if you want to increase performance on chips long term. But what we didn't know is like, what's the cost of doing that? Like, what's the ROI for somebody who's going to be put for using this technology? Are they going to have to, build a power plant next to it to power the lasers to get this performance and stuff? Or, what is the, what's the cost analysis here of implementing the technology? And that kept me up at night very early on, because it was a big unanswered question. We didn't know what the efficiencies were going to be. We knew they were very low in these bulk systems that had not been integrated through this photonic engineering process. And we knew that we could push those power densities much higher. But what would happen to the efficiency? Can we also engineer the efficiency alongside that? And now we know the answer is yes. We can actually engineer both. We can give you very, very high efficiency and very, very high power densities simultaneously. And the implication here is actually, we're still kind of coming to terms of like what this is going to mean for the industry, because what became very clear about, maybe a year or so ago, was that the efficiency was high enough that you were going to be in a situation where once that heat has been converted into light, optical energy, you can use essentially a solar panel to recover that optical energy. But the types of solar panels that you use with lasers are very different than the solar panels that we're kind of used to seeing that are put out in fields and stuff to generate electricity. Those solar panels are, limited by the Shockley-Queisser limit. In the range of like 20 to 30% is what it's what most solar panels can achieve. Okay, a laser power converter, essentially a solar panel for lasers, does not have those same limits applied to it, because you're only recovering the energy at one frequency, or a narrow band of frequencies. It's not broadband like sunlight. And so you can get very, very efficient energy recovery from laser light using these laser power converters. And these are commercially available. These things are something that you can buy now that are 60 even 70% efficient, right? So double the efficiency at minimum of a solar panel. And we've got partnerships that we're working with a collaborator to demonstrate 85% efficiency. And we know the upper bound on this, in principle it's 99, but we think we can push into the low 90s without a whole lot of additional photonic engineering, because we're just at much higher powers. And that changes the equation for what we're able to recover at what efficiency. And so what this means, though, practically, is that if you put this technology into a 100 megawatt data center, say, right, there's enough waste heat generated by the data center that you will be able to recover enough power to completely cover the cost of cooling the data center. The typical data centers take like 20, 30% of their budget goes just to cooling the hardware. Okay. Saying that goes away if you integrate laser cooling. So your data center, immediately, the cost of operating the data center is way, way lower. Okay. And so you still have to pay for the power devices. You're not getting free energy or anything like that, but there's sufficient waste heat energy that you can recover optically that allows you to completely cover the cost of cooling the data center and have enough left over. About, in the case of a 100 megawatt data center, is about 20 megawatts. So your 100 megawatt data center just became 120 megawatt in terms of its computing capabilities. Okay, so that's the pitch here. That's the ROI for the customers. Is no cost to cool your hardware, and you get 20% of your power back to feed into the chips or sell back to the grid, whatever you want to do with that electricity, because it's just electricity, right? You can do whatever you want with it.
In this case, such cloud providers like AWS should call you even at night.
Yeah. So we're trying to be we're a very early stage company, right? We're just going through our Series A financing round. We're 5 people right now. We're hiring 3 or 4 new people over the next month. But you have to be careful with the cloud people and these the hyperscalers like the Googles, AWSs, Microsoft, right? Because they have they operate at huge scales, and so that means that for their production, for them to put something into production, buy products from you, right? You have to have all this redundancy in your manufacturing pipeline. You have to be operating at the same scale that they're buying and building chips at, which we're nowhere near that today, right? We are operating at, hopefully by the end of this year, we'll be able to produce, not the end of this year, in the next 12 to 18 months, we'll have capability to do 10,000 units a month. Okay, so like nowhere near global chip scale production. But we're trying to get small scale manufacturing stood up, and then we're going after these niche markets on where basically they have very, very high sensitivity to latency in their workflow. And so you can imagine the early applications of this that we're targeting are things like edge inference devices, where like the time it takes for you to get a response from your chat GPT or whatever, is you're very sensitive to that performance. How long does it take for you to get the result back? Other applications are like in high frequency trading, or crypto is another really good example. These crypto miners, if you can double the performance of these ASICs for Bitcoin mining, right? You mine Bitcoin twice as fast as anybody else on the planet, you get a lot more Bitcoin. And so, and at the same time, you're lowering their cost of cooling. Like that's a no-brainer for these guys. And the crypto guys especially are way more open-minded. It's like the Wild West. Like they'll try anything if it's going to increase profitability, give them more resiliency and lower costs. So all that directly turns into profitability for them, and they're willing to try lots of interesting new technologies. So that's the strategy and how we're kind of going to market. And you use that as sort of a way to grow the manufacturing and scale it out, figure out what's working in the product design, and really 3 or 4 years from now is where we hope to have a fully integrated system that we can sell as a solution to the hyperscalers, to everybody, right? It goes into any server, right? But there's some co-design around how you get optical fibers for cooling into the server along with these photonic cold plates. But in principle, we can basically move that into solution engineering for a large scale integration across any data center at that point. So 3 or 4 years out from when we're going to be working with the hyperscalers and that kind of thing. But we're hoping to, in the next 18 months, to really be demonstrating this technology at small scale with select customers, in an early access program.
Yeah, it is a general question I usually ask. How do you see you 5 years later? But speaking about your technology, I think we must think about a little bit more wide boundaries. So about 10 years, how do you see it?
Yeah, that's a very interesting question. And what we found is basically once you get to that point where you are at the efficiencies required to have net, basically cover the cost of cooling, have net power recovery at the data centers, at that same point, those efficiencies are so good that you actually can compete with conventional cooling systems. And so that means like the way that you typically cool a house, like an HVAC system, right? The way you typically cool a car's engine block, right, is a radiator. Like you have a similar efficiencies to fans and HVAC, condenser loops, right? And that means that the application space explodes. Like it isn't just chips anymore. Like you could, in principle, start doing industrial cooling with lasers, and that's pretty wild. There's a whole space of thousands of materials that have not yet been explored for laser cooling. And Maxwell, we're really looking at like the long-term strategy of the company around being the core provider of laser cooling technologies. Really trying to build an industry around laser cooling. And that's very exciting to me because it's like you don't know what applications people are going to think of. We think we've got some pretty awesome ones, and we've laid a lot of the IP and groundwork for that. But who knows what's coming 10 years from now if this works the way we think it will.
Great. You foresee my question. I wanted to ask you about other industries where it could be used, not just about microchips cooling. So it really could be a revolution in 10 years.
Yeah, absolutely. I mean, it's a very exciting technology. We're the first company trying to commercialize this, right? It's very early because we're really at the bleeding edge of what's known about laser cooling and the materials and what you can do with it. But yeah, the applications for it are are exploding. Like we don't know what the limits of the application space are at this point, but it looks very, very good. It looks like there's lots of different places this could go if you reach the targets that we're aiming at.
Got it. Thank you. Thank you for your opinion. What has been the most surprising moment in your journey?
Most surprising, I guess I think the people and just like what to just how if you really double down and focus on finding the right people, getting the right people on the bus, it changes everything. I mean, for a long time early on, we founded in the end of 2020 is when we actually incorporated, and for a couple of years we avoided talking to academics. We were trying to lay down much IP. We were very concerned about if academia, if we got involved with them, it would make it was just confusing, and what would be the implications. And I think letting go of some of that fear and just kind of thinking about it as more like, hey, if this is successful, like everybody wins, and we're like everybody can make money off of it. If you're going to try to build an industry, eventually you're going to have competition around it, and like not get so hung up on just trying to get everything and not talk about what you're doing, and instead focus on trying to find the team that's going to make this thing a reality. And you're not going to be able to do it on your own. You're not going to be able to do it just by kind of finding a couple of people that are interested and might be able to figure it out. You got to find the right talent. And finding Alejandro, he's a tenured professor at Princeton, world leading expert in nanophotonics. It became very clear. I'd been following his research for years, even while I was at Cray, and his group. And it's crazy kind of going from reading about somebody and the work that they do, and kind of like you hold these people up in very high regard in your minds, and then you get to meet them, and not only meet them but start working with them and build a company with them. It's been just the degree and the rate of progress that you can make by having the right people is what's been most surprising. And just everything that we've accomplished so far and what we're going to be able to do is all because of these guys, and just the incredible talent and intelligence and work ethic. I mean, these people are hardcore. They go hard. I've never met anybody like the folks that Alejandro has brought into the fold here with us. Just next level human beings that can do anything.
Thank you. And speaking about you, Jacob, what excites you most about working on Maxwell Labs?
I'm a computer guy. Like, I like fast computers. I have been waiting for computers to get faster since I was like 10 years old. Like first one gigahertz processor that came out. I don't remember how old I was, but it was like every couple of months it was like, oh, it's 1.2 gigahertz now. The fastest one's 1.5. It's 2 gigahertz. Like there's this just like where it was like ramping up, and I was like, oh my God, like what are we going to be able to do with computers 10 years from now? And then it just stopped. And for 25 years, it just stayed. And that is very depressing to me. Like that, I cannot live in a world where computers just stop getting better. And we just kind of we do a lot of marketing and add a bunch of cores and kind of pretend like we're able to make computers faster this way. What's exciting to me is actually making computers faster. That's because what happens if you can operate computers at thousands of times the power density that they're at today, the types of problems computers can solve, it totally changes what you can address with computer simulation. The types of problems you can simulate. Think about biology. Okay, this is a really good example. Or material science. The set of all possible alloys, the set of all possible combinations of atoms to build molecules, right? The sets of all possible drugs that could interact with a person's DNA and their proteome, the proteins that their DNA codes for. All of that stuff is impossible right now. The search space is so huge, and what you need to simulate, right? You have to simulate thousands and thousands of atoms to simulate a protein accurately. And then you have to simulate all of the different ways that it could interact with a drug. You have to all the possible permutations. And so what's exciting to me is that these problems that seem intractable today and are completely outside the realm of what classical computers can touch, it's what we're waiting for quantum for, they become tractable problems. Not all of them, but some of them become tractable problems if computers get fast enough, classical computers. And so while we're still waiting on the quantum thing to pan out and give us, the next gen of computer algorithms to solve these hard problems, there's a world where supercomputers combined with this technology can solve problems that we can't imagine solving today. And that's what's exciting to me.
Thank you very much. Thank you very much for your time, for joining our podcast. I will be really happy to hear from every corner 5 years later how your technology changed cooling industry. Really.
I'm looking forward to it, man. I appreciate the conversation. It was good talking to you. And yeah, we'll keep you posted. We'd love to keep in touch.
Thank you very much, Jacob.